In this lecture, we will analyze inductively degenerated LNA. We have already studied 3 single MOS LNA, and in all those cases, the operating frequency was very small compared with the threshold frequency. So that allowed us to neglect the gate to source capacitor, and that is why all the results, they were independent of frequency. But if we have a scenario where operating frequency is not very small comparable to threshold frequency, in that case we will not be able to neglect the gate to source capacitor. That time we will have capacitive impedance looking into the gate of a MOS. So we need something to cancel out the capacitive nature of the gate input impedance, and that objective is fulfilled in this LNA. So this one is used when omega is not very small comparable compared to the threshold frequency. So this implies CGS is not 0. It cannot be taken equal to 0. It has to be included into the small signal model of the MOS. So we will carry out analysis for this case, and of course we will continue to neglect channel length modulation. That is lambda is equal to 0 or R naught is infinite. So under these two conditions, we will find out the input impedance and the noise factor of this inductively degenerated LNA. So the circuit for this LNA is this one. So this is the input impedance we are interested in finding out. So in this case, there will be gate to source capacitor here, and that is why this is in general is going to be complex if we do not have this without LS. In fact, with LS also it will be complex. So Zin is capacitive in absence of LS, so we need an inductor at suitable location, so to neutralize that capacitive nature. And it turns out that if we degenerate this source, that means if we put source not at the ground directly, but put a reactive or resistive element between this, then it leads to degeneration. And if it is inductive, this will cancel out the capacitive nature of the input impedance. So first we will find out Zin, and then we will go on to find the noise factor. So now we will have to include this gate to source capacitor in the model. And source is connected to an inductor. So what we want to know is this Zin, which is going to be Vx by Ix. right? So there will be certain current here, which we will call IM. Now to find out this ZIN, we are going to apply KVL in the input loop, in this loop. So this gives rise to, see here there are two currents. One is IX and another is IM, and both will be flowing through this LS. So here we get Vx is equal to this Ix into reactance offered by the gate to source capacitor, which is minus J by omega CGS, plus the current flowing through LS, which is Ix plus Im into its reactance, which is J omega Ls. So here we have an unknown current, this Im. So for that, we are going to write equation, which is Gm VGS. Now we need to find out this VGS, and VGS, as you can see, is voltage getting generated by Ix flowing through the capacitor CGS. So this VGS is Ix into minus J by omega CGS. So we make this substitution here, so that gives rise to Im is equal to Gm minus J by omega CGS into Ix. So we can substitute this in equation 1. X is equal to minus J Ix by omega CGS plus Ix minus Gm J Ix by omega CGS into J omega Ls. So here we see that we have both imaginary and real parts. So we can separate out the imaginary parts, which is this term and this term. So we have minus J Ix by omega CGS plus J omega Ls Ix. So these two are the imaginary part, and the third term, this term, gives rise to real part, which is Gm Ls Ix by CGS. So, and we see that Ix is present in all the three terms on the right hand side. So we can write Vx by Ix is equal to J minus 1 by omega CGS plus omega Ls plus Gm by CGS into Ls. So here we have imaginary part and we have a real part also. So in general, this is the input impedance looking into the gate of inductively degenerated LNA. And this imaginary part is frequency dependent. And one of them is positive, other is negative, so they can cancel out each other. So at frequency omega square is equal to 1 by LS CGS, this imaginary part is going to be 0. So imaginary of Z in is equal to 0, and this is equal to Z in. So at this frequency, at omega is equal to 1 by square root LS CGS, what we find is Z in reduces to a purely real value. Z in is equal to GM by CGS into LS. And we know that this factor is basically omega t. It is omega t into LS. And this is real, so this can be made equal to RS or ultimately equal to 50 ohm as well for the purpose of matching. This is going to be value. So when we do the matching, for match condition, what we will have is omega t LS is equal to RS. Right. So here, this will imply that we have a fixed value of LS. So this gets determined. And once LS is fixed, you can see that omega, the omega where input impedance turns out to be real equal to RS is CGS into LS. So if this is fixed because of the matching, and CGS is going to be get decided by the device, so then this automatically gets fixed. So for match condition, we find that the operating frequency where input impedance is going to be real will become fixed. And if we want to use this LNA at any other frequency other than this one, then we will not be able to achieve 50 ohm or real input impedance. So we do not have freedom in fulfilling the match condition and deciding the operating frequency. So these two things cannot be fulfilled separately. They are interlinked. So to decouple the operating frequency from the match condition, what is done is we introduce another inductor at the gate, between gate and source. So we now create a new circuit. we use this circuit. So here we have introduced this LG additional inductor between gate and the source, and we have our usual LS. So now we would like to know what is this new input impedance, modified one. So recall that we have already found out the input impedance of the circuit at this reference plane. This part we have already found out. So looking from here, what we find is that the new input impedance is going to be earlier one plus the impedance of this LG. Both are now in series. So here for Z in, we can write the expression that we have derived here, the complete expression. This one, this is equation 2. So here we had already found omega ls minus 1 by omega cgs plus gm by cgs ls. Now we have j omega lg, the original term. So here now we see that we have three imaginary terms, these two, the older ones, and this new. So they can be combined. So we now have omega into ls plus lg minus 1 by omega cgs and the real part. So this is the new input impedance. And this new input impedance is going to be real when this is equal to 0. So for real z in dash, what we should have is omega square is equal to 1 by ls plus lg into cgs. And at this frequency, z in dash is going to be gm by cgs into ls, that is omega t into ls. So we see that the expression for the input impedance remains same, what we obtained for the previous case. But now the frequency where this real input impedance will be achieved is given by this equation, equation 3. So here we can, for match condition, we will have to make z in dash is equal to rs. That will give rise to omega t. ls is equal to rs, implies that ls is equal to rs by omega t. So here ls gets determined or fixed, but we see that the operating frequency still has one parameter lg left, which can be used to satisfy the given operating frequency condition. Omega, the operating frequency that we want to use. However, this hasn't solved the problem completely, in a sense that uh, the minimum value of Lg is 0. That means there is a minimum frequency that can be achieved, and that will be equal to Lg CGS square root. So if we want to have an operating frequency below this one, so that cannot be done using whatever architecture we just now saw, the modified LNA. So using this technique, we can only increase the operating frequency to a certain value, but not uh, reduce. Sorry, we can decrease the operating frequency. This is not the minimum, but this is the maximum omega we can have. So for this Lg minimum, we can have a maximum omega, and that maximum omega or the operating frequency will be given by this expression. So operating frequency can't be increased, not reduced, but the operating frequency can't be so operating frequency can't be increased beyond this omega max. But most of the time, this frequency is going to be quite high. So user will very often need to operate at a frequency well below this rather than above this frequency. So for the most of the practical purpose, this modified version of the LNA will be okay. So now we are going to find the noise factor. So here if you see the circuit, so in this circuit, there are actually only two noise sources present. First is this RS, second is MOS. And we are going to assume that this LG and LS, they are lossless. But if you include their loss also by incorporating a resistor, then there will be two additional noise sources. So to keep the thing simple, we will neglect them, but their effect can be uh, analyzed by incorporating the corresponding registers. So we have to find out the short-circuited, this short-circuited current due to RS and due to the MOS. So first we will try to find short-circuited output current due to RS. And before we proceed to find this, I would like to point out that we will be using this expression very often. Keep in mind that it is only when this gets satisfied input impedance is real. So this circuit has to be used only at this frequency. That means at this frequency. And there we will have this condition fulfilled. So this, let us say equation, this auxiliary equation, say 5, will help us reduce the effort involved in finding out the noise factor. So first we want to know the effect of RS. So we draw the noise model. So here we have noise source due to RS, then LG inductor, then gate to source capacitor, so it is this ION current which we are looking for. And here we have voltage VGS. So now we have to set up equation here, and let us assume that noise current on the input side is IN. So once again we apply KVL in this input loop. So this gives rise to Vn minus In into Rs plus j omega Lg minus j by omega Cgs. So this IN current flows to these three elements, Rs, Lg, and Cgs. But through this Ls, we see that there will be actually two currents flowing, one from left side, that is In, the other from the right hand side, which is ION. So for this term, we will have to write minus In plus ION into j omega Ls is equal to 0. So we are interested in finding out ION. So what we will write is expression for ION is GM VGS. So here now we need to substitute this VGS. And we can see that VGS is voltage across capacitor because of current IN flowing through the capacitor CGS. So VGS is IN into minus J by omega CGS. Therefore, ION is equal to GM IN minus J by omega CGS. So we now have relation between IN and ION. So we can substitute this IN in equation 6 from IN is equal to J omega CGS divided by GM into ION. That is equation number 7. So 6 gives us Vn minus J omega CGS by GM ION into RS plus J omega LG minus J by omega CGS plus J omega LS, and finally minus J omega LS ION is equal to 0. So this is the equation containing the relation between ION and Vn. So here we can write Vn, and what we will do is we will now take the help of equation number 5 that we had written. So for that, here you can see that we have all the three terms of equation 5 present here. So sum of all these three terms is going to be 0. So for matched case, this 5 is valid. That means this term, this term, this term, they added together, they are going to be 0. So now we can write Vn minus J omega CGS ION divided by Gm. So what is left out here is now only Rs minus J omega Ls ION is equal to 0. So we can write Vn is equal to, and here we see that this CGS by Gm is equal to 1 by T, omega T, 1 by omega T. So this becomes omega by omega T. Rs ION plus, and here we will have J omega Ls ION. Now this Vn becomes omega by omega T Rs plus omega Ls into ION, and here we have J. Now from here we can take out omega by omega T common, J omega by omega T, and what we will have is Rs here, omega T here, Ls ION. So one more simplification can be carried out here, that for match condition, because we are carrying out all these derivation for the match condition, we found that Z in dash was omega T Ls, and that is equal to Rs. So this can be used to substitute omega T into Ls by Rs. So this Vn becomes J omega by omega T into Rs plus Rs. So ION finally becomes omega T by omega into Vn by 2 Rs, and here we have 1 by J. So this is the expression for short-circuited output current due to the source. Now we have to find out the short-circuited output current due to the MOS itself. and this we will be calling as IOD. So we draw the model for the MOS. So this desired current that we are looking for is IOD. And here we see that IOD in general will split into two currents, IM and ID. And then at the other end, they combine to again give rise to IOD. And this IOD flows through LS. No, not LS, but actually this IOD will get splitted into two currents, one into the gate side, which we will call as I1, other into source side, which we will call as I2. So here now we set up equation for IOD. So KCL at the drain, at this drain D, give rise to IOD is equal to IM plus ID. And IM is GM/VGS. So we now have this equation. So we need to find out VGS, which is this voltage. And this voltage is negative of the voltage developed because of the flow of current I1. So VGS is minus I1 into 1 by j omega CGS. So here what we will have to do, we have to write I1 ultimately in terms of IOD, because it is this IOD current which is getting divided into two parts, I1 and I2. So what we are going to do is we are going to treat this part as impedance Z2 and everything else from here and on the left side as impedance Z1. So what we are doing is we are drawing an equivalent of this part IOD at the source. So this is a source, this node. It is splitting into two impedances, Z2 and Z1. So this one is I1 and this current is I2. So this is what is basically happening. So we are looking for the expression of I1 in terms of IOD and of course in terms of Z1 and Z2. Z1 and Z2, they are known. Z2 is only this LS inductor, but Z1 is series of CGS, LG and RS. So from current division for this circuit, we can write that I1 is equal to Z2 divided by Z1 plus Z2 into the total current, which is IOD. So this is how I1 can be written. Now let us substitute Z1 and Z2 and see what we get. So I1 is, Z2 is simply J omega Ls, and then of course IOD is there in the numerator, and in denominator we have Z1, which is series of RS, LG and CGS. So it is RS plus J omega Lg minus J by omega CGS, and Z2 is J omega Ls. So this is the denominator. And in this denominator, we once again encounter the equation 5 or the expression 5. So since we are already using this for the match condition, so this part is going to be 0. So this is for match case. So for match case, I1 will become simply J omega Ls into IOD divided by RS. So now we can use this expression to find out what is going to be VGS here. So therefore VGS is J omega Ls IOD by RS, right, minus J divided by omega CGS. So this is VGS, and this you can now simplify. So omega omega will cancel out. So what we will have is Ls by RS CGS into IOD. So this is VGS. Now we can substitute this VGS finally in this equation 9 to obtain IOD. Here, so there is already one minus sign here. This part we will have to incorporate. Minus here. So there will be one more minus here and one more minus here. Now here we see that this GM and CGS, they can be combined to write omega T, and Ls and RS will be there as usual. Now for the match case, all these things are being done for the match case. So we know that this numerator, which is omega T Ls, is equal to RS. So therefore, IOD becomes minus IOD plus ID. And this implies 2 IOD is equal to ID, that is IOD is equal to ID by 2. So this says that only half of the drain current actually flows outward. And for the common gate also, we saw that not the entire ID flows to the outside of the circuit. Actually, some of the ID part circulates inside MOS. And the same thing is happening here also, because here we can see that VGS is negative. So this is negative. So this negative implies that the current direction is like this. So what happens? IM flows like this and merges with IOD to produce ID, and it again then returns back into this dependent current source. So there's a current which circulates inside it, and that is why IOD is only half of this ID. So you can see that half part of this ID actually circulates inside the MOS, and only the other half flows outward. So this is what is happening here. So, and this is happening because of degeneration. So some voltage gets generated here at the source that reverses the direction of the dependent current source in the upward direction, and it circulates inside it. So now we can find out the total short circuited output current. And therefore mean square current since these two are uncorrelated. One is from RS, other is from MOS. Both are physically independent elements. So they are uncorrelated, and this is what we get. Therefore, the output power, this is going to be proportional to this mean square current. And output power only due to RS, which we will call as PORS. That is going to be same factor beta into ION mean square. So beta we have already carried out derivation. So this is assuming the Norton model for the MOS. Therefore, the noise factor F is going to be ION mean square, IOD mean square divided by ION. And this is 1 plus IOD mean square, ION mean square. So this we can substitute. So IOD mean square is simply ID mean square by 4, because this was the half of the drain current, and denominator is going to be W by T, W whole square into Vn mean square divided by 4 Rs square. So this becomes 1 plus omega by omega t whole square into Id mean square Rs square by Vn mean square. And this will then simplify to 1 plus omega by omega t whole square into gamma GD0 Rs. So this is after substituting the expression for Vn and Vn mean square and Id mean square. So this is a noise factor for inductively degenerated LNA. So here we can see that we have 1 and we have a factor which is second order in omega by omega t. So this one is going to be very small. And this term will reduce very fast as gap between omega and omega t increases. Right. So second term contribution is very small. Now we can compare this with that of common source amplifier. So for common source amplifier, the noise factor was 1 plus gamma GD0 GM square RS. And keep in mind that this was carried out by including CGS. So now if we see that this first term, this is there in both the case. Second term is also present in the both the case. But here we have this additional term. So for common source, we have a large noise factor. And this is because entire ID was flowing outside. It was available at the output under short circuited condition. So in that case, IOD was actually equal to ID for common source case. But for inductively degenerated case, we found that only half of this ID was actually. So for ID case, only half of the ID was actually going outside. So that is why for this case we have less noise factor. In fact, if we compare this noise factor of the ID case with the remaining 3 LNAs, we will find that this has the smallest. So biggest advantage of this ID LNA is that it has least noise factor out of all those 4. But disadvantage is it is narrow band, and this can be used ideally only at this frequency. So this is the biggest disadvantage of this circuit. So now I would like to point out one shortcut for finding out ION current. So we carried out in detail, but by noting that Z in is equal to Rs, let me emphasize that we have carried out all derivation for this case only. And that is why we got simpler expression. Otherwise, the expressions would have been a lot more complicated. So for this match condition where Zn is equal to Rs, uh, we had this equal to omega t Ls. So it is this condition under which we carried out the derivation. So now if you look the model that we draw, so meaning here is that this Z in dash is equal to Rs, and ION basically correspond to this case. This is noise source. So instead of drawing the model for this entire thing, so there is actually no need to draw the model. What we can do is we can put Rs here and Z in, which is itself Rs. So the whole thing now gets simplified to this case. Yeah, and this is the reference plane for Z in. So in this case, In is simply Vn by 2 Rs. So In can be easily found out in shortcut way using this. And recall that ION was simply the current ION, short circuited current, and this was equal to this GM into VGS. So ION is equal to GM VGS. And what is VGS? VGS is IN current flowing through CGS. So VGS is IN into 1 by J omega CGS. And IN we have derived is Vn by 2R 1 by J omega CGS. So ION turns out to be GM into Vn by 2R 1 by J omega CGS. So here, this is how we could have arrive at ION, and the main thing that help in taking this shortcut is this observation. And at this case, J omega Lg plus Ls minus 1 by omega CGS is equal to 0.